Hello dear students, welcome to Thermodynamics part 12 series of videos you will find on the channel Learning Chemistry is Fun. We have earlier spoken about enthalpy. In this particular topic we are talking about specifically bond enthalpy. Now bond means friendship, coming together of two or more atoms to form a friendship. Now, when a chemical reaction takes place, bonds have to be broken, new bonds have to be formed. So, when I talk about bond enthalpy, this could talk about the enthalpy change when a bond is being broken or when a bond is being formed. Now, that becomes very confusing when we say only bond enthalpy. Which bond enthalpy are we talking about? Are we talking about the bond formation enthalpy or the bond dissociation enthalpy? To avoid that confusion, we have defined bond enthalpy in a specific way. The enthalpy change when 1 mole of the bonds are broken in a molecule in gaseous state to give atoms in again the gaseous state. Now here, if you notice, the stress is on the form of the reactant and the product that we are talking about. So you have the molecule in the gaseous form and you have the product also in the gaseous form, and we are talking about the breaking down of 1 mole of the bonds. We are talking about breaking over here. You will come across texts and books and literature where it could also talk about the formation of 1 mole of the bonds, but you will realize that in that case the values, the magnitude remains the same, only the sign changes. Why? Bond breaking is a process which is endothermic. You need heat in order to break a bond. You need energy in order to break a bond. In order to break the friendship between two people, you need to input some form of energy, right? So the same thing happens over here. It's an endothermic process. That means the enthalpy change is positive. On the other hand, bond formation, coming together of two atoms to form a friendship, is an exothermic process. It's a relieving process. You relieve your energy, you relieve your tensions when you are with friends. The same thing happens over here. So delta H is negative over here. There is release of energy. So if you notice, both of them will require the same amount of energy, but in one case energy is absorbed, in the other energy is released. So magnitude remains the same. So if I talk about two H atoms coming together to give me H2 gas, then the enthalpy change would simply be negative 434. Here in this whole lesson, I'm taking it as the bond dissociation process. So hydrogen, which is in the form of a gas, breaks down to give you two hydrogen atoms, again to be taken in the form of a gaseous molecule. The enthalpy change, the standard molar enthalpy change is 434 kilojoule per mole. Same way for oxygen, it is 498. Again, we have to stress on the gaseous form of a substance. We are starting with the gaseous form of the reactant and we are getting the gaseous form of the atoms. So, we have taken the examples of diatomic molecules, that means molecules which are made up of two atoms, and if you notice over here, the enthalpy changes are varying. Now this enthalpy change H2, it involves a single bond between two hydrogen atoms. Oxygen on the other hand involves double bond between the two oxygen atoms. Nitrogen on the other hand involves triple bond between the two nitrogen atoms. If you see the enthalpy changes, they are indicative of the type of friendship which is there between the two atoms. Hydrogen 434, oxygen 498, nitrogen 946, all in kilojoule per mole. The value for nitrogen is the highest. which is indicative of its chemically inert behavior as well. In other words, in order to get the two nitrogen atoms to separate, you need to input a large amount of energy. That is why in your other topics you would have studied that nitrogen does not undergo chemical reaction very easily. This is very easily explained by its high bond enthalpy. In other words, we need a large amount of energy to break this bond. Coming to polyatomic molecules. Now here we've spoken about molecules made up of two atoms. Now this can be homoatomic, this can also be heteroatomic. So for example, HCl. It's a diatomic molecule but hetero. So same way you will have the enthalpy value for it. In the case of methane, CH4, if you notice there are 4 bonds, hydrogen, hydrogen, hydrogen and hydrogen. All 4 of them are single bonds CH. It is observed that the value of each bond enthalpy is different. So when I take away the first hydrogen atom, the bond enthalpy, now all of these are listed in kilojoule per mole. Just to avoid too much of kilojoule per mole, I have written it in the heading, bond enthalpy, standard bond enthalpy as in kilojoules per mole. The first hydrogen atom breaks, 427 is the bond enthalpy. The second hydrogen atom breaks down, so we have the second bond enthalpy, that is 439. If you notice, there is a difference in these values. Go on to the removal of the third hydrogen atom, this rises even further. What does this indicate and why is it happening? If you notice over here, once you remove one hydrogen atom from here, all the electron cloud of the carbon is concentrated towards the remaining 3 hydrogen atoms. It wants to hold them tightly. Oh, let me not get them away from me. So, you need more energy in order to separate the second hydrogen atom. Oh, you've managed to remove the second one as well. It wants to hold tight onto the other 2. So, this explains why the bond enthalpy is increasing at each step. Although if you notice, the last one, 347, is very low even compared to the first one, because the species has now become very unstable. The electron cloud of the carbon is now very much susceptible to attack by other atoms and molecules. So it becomes 347. Now, which of the 4 bond enthalpies are we going to talk about? If you ask me which one of these is the CH bond enthalpy actually? First, second, third, fourth. All these are varied values. To avoid this confusion, we introduce a term called as mean or average bond enthalpy. As the name indicates, mean means you take a sum of all these enthalpy values divided by the total number of CH bonds. So 1, 2, 3, 4. We've spoken about the breaking of 4 bonds. So total of this divided by 4 gives me the mean bond enthalpy. These values specifically are called as the bond dissociation enthalpies in this particular case. So this is the bond dissociation enthalpy of the CH bond in step 1. Step 2, that is for the third hydrogen and the removal of the fourth hydrogen. Whereas this in general is the CH bond enthalpy. So when you see the tabulated values for polyatomic molecules, you understand that those are actually average values. Those are not the specific values, because as we have seen, the bond enthalpy or bond dissociation enthalpy changes with the nature of the atoms which are attached to the central atom. What is the relevance? What is the significance of bond enthalpy? Why are we studying bond enthalpy? Bond enthalpy gives us an idea about the bond length, the bond order, and the stability of the molecule. Although there are other factors as well. Higher bond enthalpy means you need much more energy to break the bond. That's what we've seen in the case of nitrogen. So that means it's a strong bond. Strong bond means they're close to each other. So what we have is, if there is a single bond between the two atoms, double bond between the two atoms, triple bond between the two atoms, so they come closer to each other. So closer the friendship, stronger or more is the energy required to break the bond. And since they are coming closer, the bond length, the distance between the nuclei of the two joining atoms will be shorter. Greater will be the stability. This is very much clear if you see the bond enthalpy value for nitrogen and oxygen, 498 and 946. This very clearly explains also why nitrogen is chemically inert. The bond length for nitrogen is 110 picometer, for oxygen it is 120. How are we going to use bond enthalpy in thermodynamics? It's very interesting. We've talked about the enthalpy, the standard enthalpy change for a reaction. A reaction which involves a conversion of reactants to products. Again, gaseous and gaseous. We are not talking about the other states because we are talking about only bond enthalpy. We'll take small baby steps and then go on to changing the state as well. So when you talk about the standard enthalpy of a reaction, this is nothing but the standard enthalpy of formation of products minus the standard enthalpy of formation of reactants. Now here in the case of reactants, bonds are being broken. In the case of products, the bonds are being formed. So when the bonds are being formed, I am talking about the negative bond enthalpy of products, because bond formation will be opposite to bond breaking. When we are talking about reactants over here, now in the case of reactants, bond breaking is taking place, but we are talking about the enthalpy of formation. So we take minus bond enthalpy of reactants. Open the brackets, negative becomes plus. We can rearrange these values and we get the standard enthalpy change for a reaction, or the standard molar enthalpy of a reaction would be the bond enthalpy of reactants minus the bond enthalpy of products. This is one point where many students face the confusion. Please remember, when we are talking about the enthalpy of formation, then it's enthalpy of formation of products minus the enthalpy of formation of reactants. But when we are talking about this equation in terms of bond enthalpy, then it is, yes, reactants minus the products. You have to be very careful about this. There is a difference in the enthalpy of formation and the bond enthalpy. Please don't get confused between the two. You will, if you go through the previous videos, I have explained the enthalpy, the standard molar enthalpy of formation of a substance very clearly in steps. Coming to factors affecting bond enthalpy. What are the factors which will decide whether the bond enthalpy will be high or low? Very clearly we can see hydrogen, oxygen, nitrogen. Let's start with hydrogen and oxygen. Obviously the atom of oxygen is bigger than that of hydrogen. So if you notice over here, the size of the atom plays a major role. Smaller the atom, more the enthalpy change, because the force of attraction between the nucleus and the electrons will be strong. Just now I mentioned about hydrogen and oxygen. Now according to this logic, the size of the atom of hydrogen is smaller than that of oxygen. So the bond enthalpy of hydrogen should be more. Then why is it that for oxygen it is more? Can you think of a reason? Post your answers in the comments and let us see. Coming to the type of bonding. Single bond between two carbon atoms, double bond between two carbon atoms, triple bond between two carbon atoms. If you notice, the bond enthalpy increases with successive steps. Here we are talking about identical bonds, identical atoms over here. It is just that the type of bond is changing. So if you notice, with increase in bonding between the two atoms, the bond enthalpy actually increases. As we said, stronger the friendship, more is the energy required to break that bond. Electronegativity difference. Now here, electronegativity difference, if you notice we are talking about here C double bond N. That means if we are breaking the bond between carbon and nitrogen, they are doubly bonded. Or carbon and oxygen, again they are doubly bonded. The standard value for the bond enthalpy of C double bond N is 615, whereas for C double bond O it is 741, which is much higher than that for C double bond N. The constant factor over here is C and the double bond between the two atoms. What is changing is the atom to which the carbon atom is bonded. So it's nitrogen and oxygen. As you go along the periodic table, you know that electronegativity actually increases because of the decreasing size of the atom. So oxygen is going to pull the electrons more strongly. It has a stronger pull towards the electrons compared to nitrogen. With the result, the C double bond O becomes stronger because of the electronegativity difference between carbon and oxygen, which accounts for the high bond enthalpy for the C double bond O. Hope this makes the concept clearer. After watching this video, try and attempt numericals based on bond enthalpy and enthalpy of a reaction. But when you are doing the numericals, be careful that your reactants and the products have to be in gaseous form. If they are not, so let us suppose one of your reactants is in the form of a solid. So in your calculations you add one more step. You convert that solid into gas first, take that enthalpy into account, and then go on to do your calculations. That is why I said we will take small baby steps at a time. So probably you could start with the easy numericals and go on to the difficult ones. I shall also be taking up a few numericals just to make the concept clearer in the next video. Till then, happy studying. If you find the channel useful, please do subscribe. You will also find material on Learning Chemistry is Fun, which is a Google site. There will be supporting material on the videos that are posted on the YouTube channel Learning Chemistry is Fun. A very simple identification of the channel is a smiley over there. Enjoy studying.